So with last time with the translational partition function, remind me again in your own words, what is the partition function?
Normalization.
So what?
It's the denominator.
Okay, denominator of the Boltzmann distribution, sort of the probability calculation as to, and so that denominator, another word for that denominator in this statistical analysis is what? It's the sum of all the possible Boltzmann factors, okay? The normalization constant. So it's all possible outcomes. So it's that normalization constant in the denominator of the probability calculation. But what is another concept associated with the partition function?
Unitless.
It's unitless. Okay. But like if I have a partition function that is 5 and another partition function that's 1, what can I say about the one that's 5? What is that number telling me?
Levels?
Something about the levels. What is it telling me about the levels? So the system that has a partition function that's 5 is different from the system that has a partition function of 1 in what major way?
There are 5 occupied orbitals.
Yeah, it's sort of an idea of how many not orbitals, but levels are populated. So 5 energy levels are populated if the partition function is 5. Yeah, so it's telling you, and again, so go back to that normalization constant. It's in the denominator of the statistical evaluation, and so there's 5 possible outcomes, right? And if you're looking at probability, you have the energy level you're interested in divided by all the possibilities, and in that case, all the possibilities is 5. If you have a system with a partition function of 1, that means there's only one energy level populated, and statistically there's just one possible outcome, and they're all going to be in the ground state in that case. And for translation, just review from last time, what was the estimate of the room temperature translational partition function for argon? Just give me an order of magnitude. Was it 10, 100, 1,000, 10 to the 6th?
10 to the 24th?
Yeah, 10 to the 30th, 10 to the 24th. It was 10 to the huge numbers, okay? And that's telling you how many translational energy levels are populated by a gas at room temperature and 1 atmosphere pressure. So that's amazing that, you know, another way of saying that is that we really can't detect translational quantum effects because the energy levels are so close together that at room temperature, 1 atmosphere, they're 10 to the 30 are populated. In that calculation, if you go on in the supplemental material, there's a calculation at what temperature would the translational effects become a 2-level system where you just have 2 energy levels populated. And the answer is like 10 to the minus 11 Kelvin. So that's why, again, we can't really observe that because it's difficult to get something down to that temperature. Remember how you cool something down. You put something hot in contact with something colder. It sucks the heat out of it. What are we going to put the system in contact with that's going to suck the heat out down to 10 to the minus 11 Kelvin? Right? You almost have to start with something that's at absolute 0 to get it. And where are we going to find absolute 0 in the laboratory? We can in vacuum get very close. We can have little confined gases and we let all the hot molecules escape. Because in that little cluster of gases, there are a few molecules that are in the ground state or close to it. And that means they're really, really cold. So if we let all of the hot ones leave, hopefully we have enough that we can observe their effects. And we're starting to see that. So we're starting in super cold, they're called Bose-Einstein condensates, that these little condensated gases that we can see these quantum effects starting to emerge in confined translational particular gases, and we do that in high vacuum, and it really it's not so much a test of how we can cool things down as it is a test of how we can detect the small number of gases in a vacuum, right? Because there's some cold atoms in this room, okay, that have 10 to the minus 10 Kelvin temperature. I mean, they're just barely moving, because they hit a molecule at a glancing angle and gave up their energy, and now they're just barely moving. And so they're down in the ground state for translation. But how could we detect them? That's the key. We really don't have the detection ability to collect those and observe their properties. So now we're going to rotational motion. So this is again molecules rotating. This brings in the moments of inertia and the rotational constant we used last semester for like the carbon monoxide lab was a big deal to determine B. The spacing in the row vibrational lines was 2 times the rotational constant. So we're still using those kinds of ideas of rotational motion being quantized. And in this case, we have the energy equation. E is equal to the rotational constant times J plus 1. So that's familiar to you. And that rotational constant B is h over 8 pi squared, the speed of light times the moment of inertia, I. And that moment of inertia for a diatomic is just the reduced mass times the bond length squared. So mass is in the denominator of that rotational constant. And so is size of the molecule. So small masses and small molecules will have large rotational constants. So the molecule that has the largest rotational constant, we'll see this at least 3 or 4 times in this lecture, and that is hydrogen. It's the smallest masses and a pretty small bond length. So that gives you the largest rotational constant. And so we could add up our partition function by summing up all of the Boltzmann factors for all of the rotational levels. Now what's interesting in this case is we have a function for the degeneracy. That G value in our Boltzmann factors is actually 2J plus 1. So this right here, in our previous equations, this term right here is the degeneracy. And it's a function of J. So that little piece right there, that 2J plus 1, that's the degeneracy of rotational motion. And then this is that Boltzmann factor piece right here. E to the energy over KT, and the energy is given by the rotational energy equation. You know, last time this was the translational, particle in a box energy equation. For rotation, it's the rotational energy equation. And for vibration, next, it's going to be the vibrational energy equation. Okay, so when we're dealing with these independently, we have translational motion, which is different than rotation, which is different than vibration. So it's still the same kind of degrees of freedom that we talked about in the fall. Do you remember that? Well, for molecules, hydrogen, again, is the smallest molecule, the one with the largest rotational constant, and that rotational constant is 60 wave numbers. So the largest value of B is 60 wave numbers. And remember, at room temperature, we have 200 wave numbers of energy available at room temperature. And so we're going to have excitation in all molecules for rotation. So they're going to be excited, and in fact, the difference in J is infinitesimal. So once again, we can convert from a discrete sum, to an integral. You could get into Excel and put in all your quantum numbers and add up all the energies and calculate these explicitly, and you could see the probability of population is pretty large for a huge number of them. And so, at high temperatures, we can just convert this to an integral. And so then we can integrate this equation with respect to J. So we're integrating with respect to J, and out comes this result. So the rotational partition function is essentially KT. This over HC converts that to wave numbers, essentially. So K over HC is Boltzmann's constant in wave numbers times temperature divided by the rotational constant. Or if you were to take just this piece right here, B, and divide it by that Boltzmann's constant in wave numbers, then you would get a temperature unit for your B value, and we call that the rotational temperature. So this theta B, which is just B converted from wave numbers over to temperature, so that we can just directly compare it to the temperature of the system. And so it's just nice, instead of working in energy, we're always talking about temperature, so we can just convert everything over to temperatures. And so we have a thing called the rotational temperature. And so I'll go ahead and put the numbers on here. This is just equal to B, and I'm going to put a tilde on top, which means it's in wave numbers, right? divided by the 0.695. Wave numbers per Kelvin, and so the Kelvin come up on top, and so then you have that rotational constant expressed in Kelvin. And then you compare that to the temperature of the room in Kelvin, or the system in Kelvin. And that's your partition function. So if my rotational temperature, let's say room temperature, let's estimate it as 300 wave numbers instead of 298. Okay, 300 wave numbers, and if my rotational temperature is 300 Kelvin. If my room temperature is 300 Kelvin and my rotational temperature is 60, like for hydrogen, okay, then 300 over 60 is 5, okay. So my partition function is 5 for hydrogen. So the rotational, there's essentially 5 rotational levels excited at room temperature for the hydrogen molecule. You see what I mean? And that's going to be, in the average population of those levels. There'll be some up in the 6 and 7 level populated, but it's less probable. And the ones below 5 will be more probable. But so this would be an estimate of the number of energy levels that are populated. Any questions on this right here? Notice this trend. We did the same thing for translation. We started with the quantum sort of energy equation, n squared, h squared over 8ml squared. And we said, look, this is a sum, but that's a really long sum. And they didn't have HOCl in the back in the day. So they made the assumption that n, the changes in n quantum number were infinitesimal, and so we'll just turn it to an integral. Okay. And then the same with rotation. Again, it could be an infinite sum, but we'll just turn it into an integral and make this estimation. So diatomics are the smallest molecules. Let's look at the rotational constant. So this is some review, looking again at mass in the denominator and size or bond length in the denominator. And so we have all of that. Remember, that whole portion doesn't change and is roughly equal to 16 grams per mole, angstrom squared, wave numbers. That way you can use grams per mole for your reduced mass, and you can use angstroms for your bond length. And so you can come up with these rotational constants very easily. And so here's a little table coming up. So here's the hydrogen rotational constant, HCl, DCl. Look at the change it makes by putting an extra neutron on that hydrogen. Again, because the reduced mass is really the mass that's moving. So if you calculate the mass of HCl, the reduced mass, it's pretty close to just 1 because the hydrogen's moving around the chlorine. The chlorine's not really moving. You add an extra neutron to that hydrogen, you've essentially doubled the mass that's moving, and so then your rotational constant gets dropped in half, okay, because mass is in the denominator. And then when you get to iodine, look what's happened. Now we have 2 masses, they're equal, and they're 127 grams per mole. Okay, and so that's in the denominator, so your rotational constant is really low. If we took that 0.03 and divided by 0.695, can someone do that real quick on their calculator? 0.0, let's say 0.0, yeah, you can type it in, 0.03735 for iodine, and divide by 0.695.
0.0537.
Okay, so this is equal to 0.05, I'll say 4, okay, Kelvin. That's theta B. So that's the rotational temperature for iodine. So now we can compare that to room temperature. How many energy levels are populated at room temperature for iodine, these rotational energy levels? We're taking 300 and dividing by 0.05. So we're essentially multiplying 300 by 20. Okay. So 6,000, what is that? Yeah, 6,000 energy levels for iodine, rotational energy levels are populated at room temperature. Yeah. So, again, the difference in J value is infinitesimal. Right? For hydrogen, you could count. Okay, so maybe that assumption fails a little bit for hydrogen, but it's certainly a good assumption for iodine. And so the Boltzmann constant can be used to convert any of these energy values into temperatures, so we can do that. So for the hydrogen rotational temperature, it's 87 Kelvin. All right, and so now let's look at a asymmetric molecule. This is the output from Gaussian. And so that's part of the reason why we're doing this statistical thermodynamics. This actually is a whole course, statistical thermo. It's a pretty hard course because it's a lot of the calculus related to these degrees of freedom and calculating the thermodynamic properties. We're shrinking it down, I guess, to the bare minimum so that you can understand what Gaussian's giving you. And so I'm just giving you enough to understand the output from Gaussian. So if you do a vibrational calculation in Gaussian, a frequency calculation, you have that thermochemistry section. And so this is the beginning of that thermochemistry section. And what do you see? You see the temperature that you've done the calculation at, which you can change in the input, actually. So you can do a vibrational analysis at different temperatures and different pressures. So it's telling you, you did this calculation at 298.15 Kelvin, which is room temperature by definition, and 1 atmosphere by definition. And you can change the isotopes. And if you just go with the defaults, it goes with the most abundant isotopes, not the average, because how can you calculate an average atom? So Gaussian's calculating a particular isotope. So it's doing carbon 12, oxygen 16, hydrogen 1. So it's not taking into account any carbon 13s unless you tell it to. But you would have a calculation for carbon 12 molecules, and then you had to do a separate calculation for the carbon 13 isotope. And if it was multiple carbons, you'd have to tell it which atom was the carbon 13. And so you can do all of that, but again, it's tedious. It's not hard, but tedious. And so then the next section, it talks about the molecule being an asymmetric top. It tells us the rotational symmetry number, which we'll see in a minute where that goes. And then it gives us the rotational temperatures and the rotational constants. So it calculates those for you, and that's kind of nice. But look at the units that it gives us. First, it gives us rotational temperatures, and until today, you probably wouldn't know what that was. So that's why I'm talking about rotational temperatures, because here you have it in Gaussian. You're like, where did that come from? It's just the rotational constant turned into Kelvin using Boltzmann's constant. And then the rotational constants are calculated in gigahertz, not in wave numbers. Okay. Essentially, there's 30 gigahertz is one wave number. So you can convert those pretty easily. We'll see that right here. So we've got that rotational constant, 645 gigahertz, which is 10 to the 9th per second. And if you just convert that over to wave numbers, you just divide by the speed of light in centimeters per second, and you end up with wave numbers. So it's 30 gigahertz per wave number is essentially the conversion. And so the net rotational constant, 645 gigahertz, is 21.51 wave numbers. And then dividing that by 0.695, which is Boltzmann's constant, we can convert it to a rotational temperature. And we see the result, 30.95 Kelvin, and that matches what we have, at least to the digits that we used, the output in Gaussian. So that's where those rotational temperatures came from. It's just reporting the rotational behavior in two different units, Kelvin and gigahertz. Because I'm a spectroscopist, I always write my rotational constants in wave numbers, because most of the time my x-axis, if it's in infrared or Raman, is in wave numbers. Old school days when they first wrote Gaussian, everything was in gigahertz. So they just had frequency, that's the x-axis. So, all right, so now let's look at the 3D rotational partition function. So that was just one dimension, and for a diatomic, you only have two rotations that are defined. Because in a linear molecule, rotation off the axis, there's no masses off the axis, and so you can't tell it's rotating. And so you just have this rotation, and because it's a symmetric molecule, C infinity V or D infinity H, those rotational constants are the same. So even though we talk about one rotational constant for a diatomic, there's really two. They're just the same. We label the rotational constants A, B, and C, and for a diatomic, A is not defined, and B equals C, and so we call it B. So that's where the letter B came from. If you notice here, for an asymmetric molecule, we have A, B, and C. We have three rotational constants. So for, again, three-dimensional rotational partition function, and also we don't want to overcount these energy levels if we have a symmetric molecule like D infinity H molecule. So we need to divide out the overcounting. Remember, this is a normalization piece for the statistical analysis of the number of energy levels that are calculated. And if the result is going to make that normalization constant too high, then we need to reduce it some way. And so since this molecule is symmetric, you can't really tell the difference if you were to exchange the two atoms. And so there's two ways to build the molecules, another way to say that. And so we divide that denominator by 2. So that's the symmetry number. For symmetric molecules, we need to reduce that partition function. And so you can see that sigma in the partition function equation. So for like A2 type molecules or D infinity H molecules, homonuclear diatomics, that sigma is 2. So we're just reducing that partition function by a factor of 2. For asymmetric molecules, or I would say heteronuclear diatomics, C infinity V molecules, that symmetry number is just 1. So we don't have to reduce it. I have not figured out a way. I'm sure it's in some textbook somewhere, but I don't know off the top of my head how to come up with a symmetry number for molecules. I know benzene, the symmetry number is 12. I exactly know why. Okay. I mean, it's something related to all the different symmetry elements, and I just never pulled that thread. Okay. So, you know, that symmetry number, there must be a way to figure that out. I just, at this point, don't know it. And then you have the 3 rotational constants, and in this case, they're converted to rotational temperatures. So that's what that theta A, theta B, theta C is the rotational temperatures for the A rotation, the B rotation, and the C rotation. So this would be for a 3-dimensional molecule, something that's not necessarily a diatomic. It reduces to the simple form for diatomic. And you can see, again, temperature cubed because there's 3 rotations, but then that is a square root of all of the temperature and rotational constant piece. So temperature is, again, to the 3 halves, just like it was in the translational partition function. And so, you know, we have that 200 wave number thermal bath at room temperature, and so we can compare that to our rotational temperatures that we get, and we can see when there'd be substantial excitation or not. So let's look at the total here now, the rotational partition function. We can calculate it for this molecule. You take in all 3 rotational temperatures, you have room temperature cubed, take the square root, multiply by pi. The symmetry number is 1 for this asymmetric molecule. And so you end up with 2230. 2230 what? What are the units on that? It's unitless. Okay. Just making sure. When you see a number without a unit, you always ask, wait, is there a mistake there? You know. But yeah, the temperatures all canceled. So there were 3 temperatures and 3 rotational temperatures, so those are gone. Pi is unitless, and the symmetry number is unitless. So there are no units in the partition function. Now, this is a function of temperature, and so as temperature goes to 0, what does the partition function go to? That was one of our Kahoot questions. It's either 1 or 0, and it goes to 1. Yeah, because again, think about it, it's the number of energy levels that are populated. So when the temperature goes to 0, we crush down to the ground state, and it goes to 1. The only exception to that is if the ground state's degenerate. Okay. Then as you raise the temperature, you go through this period where you're doing discrete sums, and that's represented here by the summation. So at low temperatures, you could add up the individual energy levels because there are not that many. But then eventually it transitions into the integral or infinitesimal difference between the rotational levels, and you have this other function that takes over. You can see there's no abrupt change when it goes from one to the other. Okay. All right, so let's move on to the vibrational. And you'll see some similar things, but this one is interesting. There's a couple of unique things about the vibrational partition function. The translation and rotation seem very similar. You have an energy equation and it turns into a summation and then you get a really simple result. But it's that approximation that you're going from a discrete sum to an integral. That's the assumption that you're allowed to do that. Okay, so let's think about vibrational motion. This is a harmonic oscillator, so we have that parabolic potential energy equation, and we have equal spacing between the energy levels. This is an important factor in analyzing vibrational motion. This is the default assumption for vibrational motion, but it does fail with internal rotation. So think about ethane, right? That internal mode of vibration, where if it's gauche, it's vibrating like this, but at higher temperatures they can spin freely. So when it transitions from being trapped to spinning freely, those energy levels are really close together. And so it's not an equal ladder of states in just that motion. The CH stretch will be, because the CH stretch is just going to be a harmonic oscillator. But the one vibrational mode in ethane, and how many are there? 3n minus 6, right? So you've got the CH stretches, you've got the CH bends, you've got the carbon-carbon stretch, you've got the deformations of the methyl groups. All of those are harmonic, equal spacing in the energy levels. But that one motion of the twist can snap over, and because that's not harmonic, that potential doesn't go to infinity, because there's a point where it snaps over to the next one, right? And so internal rotation doesn't have this infinite potential. And so that we call that hindered rotation. It's trying to rotate around that sigma bond, but it's bumping in to the hydrogens. But at a high enough temperature, it can rotate. So sometimes it's free and sometimes it's not free. And so those energy levels are not equally spaced. What happens then is that they get closer together, and so you just have more energy levels populated. So our estimate of the partition function is just going to be a little bit lower, because we might have more energy levels populated by that internal rotation, hindered rotation we call it. Very simple energy equation too. It's the vibrational frequency in wave numbers, okay, times the rotational quantum or vibrational quantum number plus a half. So v plus a half, that's the quantum number part. So if we did an integral here, we would be integrating over v. Okay, but it turns out we don't have to integrate. So let's look at this. This is kind of interesting. So there's our energy equation, and we have where do we put the zero? Where do we label zero? Well, there's two options actually. We could locate it at the ground vibrational state, v equals 0, and that's the traditional way to do it. And then we have v equals 1 on the next one. Come on, quicker. So, which gives us the energy 1, which is essentially the vibrational frequency. And then the next one is 2 times that energy, because it's equally spaced, and 3, and then 4, and so on. And so what we end up with is that sum down that you see down at the bottom. And now we could also label the energy 0 at the minimum of this potential energy surface. Now, why on earth would we want to do that? Because you can't actually occupy that space. So we can't get a molecule below v equals 0. So that seems like an option we would never have at our disposal, right? But in Gaussian, you can calculate that potential, okay? And when you know that potential, then you know the minimum of that potential. And you can add in that 0-point energy or not. And what we can do is we can compare molecules in Gaussian that are interacting with each other if we use that bottom of that potential and then add in the 0-point energies. Because think about labeling 0 as v equals 0, you've got different definitions of 0 by different molecules. Whereas if we label the minimum of that potential surface, then that's going to be the same for different molecules. So I guess that's the point, is whenever you're comparing different molecules in Gaussian, you would want to use that bottom definition. But if you're just working within the same molecule, you would use the v equals 0 definition. But either way, Gaussian gives you both. So let's look at this partition function. again, a discrete sum over all of these vibrational levels would be the Boltzmann factor for the ground state, V equals 0, which is shown here. So this would be, V equals 0, V equals 1, V equals 2 is for this one, V equals 3, and on up. Now, how do you know if you're doing this sum? So just to review, this was V equals 0, 1, 2, 3, 4. How would you know where to stop? Like, let's say you were doing this in Excel, and you had that formula and you're calculating. You got the V quantum number in the column, and then you got the energies, and then you're just adding this up. These are the Boltzmann factors. These are essentially relative probabilities of being in that state at that temperature. You would just go, like say the first one is 5, and the next one was 3, and the next one was 1, and the next one was 0.1, 0.01, 0.001. You see what's happening? As you go up in excitation, the probability of being in that level. And so you're saying, well, what contribution is this last one giving if the first one's 5? And so if you go down to like 2 orders of magnitude, you're probably good, right? If you're wrong, you're only wrong in like the ones place. If you've got hundreds, you're 1% error basically. If you want 1,000th or 0.1% error, then you would go for 3 orders of magnitude. So if the first one was 10, you might go down to 0.1. Okay, but if the next factor that you calculate is less than 0.1, then you're done with the sum. Okay, you're adding in something that's 1,000th of the first term. It's really irrelevant. So all of the ones beyond that are not really going to contribute much. So that's how you would tell it to end this discrete sum. Okay. But it turns out you don't have to do it that way. Some infinite series do converge. So this goes back, remember calculus 2? I think it was calculus 2 when you started getting into limits and series, and I know you're like, oh, don't. Okay. So if you look at this, you're like, wait a minute, I recognize that. No, you don't. I know you don't. Okay. That is the sum of an infinite series, right? 1 plus x squared plus x cubed, ... converges to 1 over 1 minus x. And so you got the actual result of that infinite sum. And so you don't have to do this in Excel term by term. You just need to know what x is. And in this case, x is that e to the minus epsilon 1 over kt. And so there's our partition function. And it's an exact result for the vibrational levels. And so let's look at the ramifications of this. Essentially, we have these energy levels diagrams shown on the right of different partition functions, and that Boltzmann distribution probabilities are shown by the blue bars in here. So this is just kind of a graph of the number of energy levels that are populated based on different temperatures. And so this is these numbers here are beta epsilon. So essentially, it's energy over kT. So the vibrational energy over kT is 3. That means the energy level is 3 times higher essentially than the temperature you have available. So let me go ahead and make this a bit simpler. This I've plotted in yellow here the temperature. So if this is the spacing, the energy I have available is right here, this tall. And since beta epsilon, or the vibrational frequency over kT, is equal to 1, then the temperature I have is giving me enough energy to populate that energy level. Like they're equal to each other. Okay. And what's interesting is if you calculate the probability of each of these levels being populated, the blue bars are telling you the probabilities. So even though I have a temperature that matches the energy level spacing and that vibration, I could actually have some population up to the 3rd and 4th vibrational level. And that's what we saw with iodine. So if you remember the iodine lab, the vibrational frequency for iodine was around 200, 214 roughly. And what is the thermal energy we have at room temperature? 207 wave numbers. And y'all had a series of V equals 0s up to those levels, V equals 1 up to those levels, the double primes, and V double prime equals 2 up to those levels. So even though we had technically only enough energy to populate the first excited state, 200 wave numbers, we had quite a few molecules in the second excited state. The V double prime equals 2 levels were populated. And then really there were some V double prime equals 3 buried in there, but I didn't ask you to assign those. Okay, there's a CHEM Ed article that talks about assigning the vibrational spectra for iodine, and they actually have the V double prime equal 3 series and 4 in there. So you can actually see where those peaks show up. They're just too small to see, but they're there. And this is a nice article. So then if we go again, so the energy level spacing is about 70% of the temperature available. And so now we're above that. The temperature gives us enough energy, more than enough, to populate that first level. And you can see how high the probabilities go of being populated. Now we're at the V equals 0, 1, 2, 3, 4, 5. So the V equal 5 is substantially popular, or it has some in it. And then if we go to the temperature 3 times the energy level spacing, then look at how high it goes. So once that temperature gets hot enough, then you can put a lot of molecules in a lot of different vibrational energy levels. The rule of thumb is when the temperature gets to be 10 times that spacing, then the difference in vibrational quantum numbers is infinitesimal. That's when we sort of make that integral change. So this is a plot of that function. Again, it goes to infinity at high temperatures and it goes to 1 at low temperatures. So as the temperature, and so what if I gave you this equation? It says, what does Q do with temperature as temperature goes to 0? So this is an important skill that I want you to have. So I've done this in 4 steps, and this would be great. If you did this on an exam, it would be beautiful. I mean, I would write awesome by it, And so I ask you the question, as temperature goes to 0, what happens to Q? Look at temperature, it's buried. It's buried in there. So you've got to look at this equation and read it like a paragraph. So you find temperature in there and you say, okay, this guy right here is going to 0. And you just work your way out of the pit. So this temperature is in a fraction, right? Here's a fraction. It's in the denominator of that fraction. So if this goes to 0, that fraction goes to infinity. And so then you would write this next. You would say, as temperature goes to 0, this fraction goes to infinity. Now you can do that, right? And then you see if that fraction goes to infinity, what happens to the next step? I've got e to the minus infinity. And if E bugs you, think of 10. 10 to the minus 5. 10 to the minus 10. It's getting smaller. 10 to the minus infinity is 0. Right? So e to the minus infinity is 0. So this piece would go to 0. And so where is that piece? It's down here, and I've got it subtracted from 1. So I'm essentially taking 1 minus 0, which becomes 1. And so I have 1 over 1. And so then Q goes to 1. Do you see how we walked our way out of that pit? We found temperature in the equation and we said, what happens? And I just worked my way out just using simple mathematical reasoning. If you can do that with equations, that's like ninja skills. I mean, that's, other people look at that and shut down because they're math phobic. Right? This is an easy question. As temperature goes to 0, what does Q do? And if you're math phobic and you look at that and you go, I'm going to skip that one. When really it's one of the easiest ones you can do. If you can determine if the denominator is infinity or 0, what's going to happen to the equation? So don't shut down when you see an equation. Most of you don't. I mean, you've gotten this far, right? But still, I'm just saying that there's a tendency to say, oh, that's a hard one, when it may not be. Right? All right, now let's say, what happens when temperature goes to infinity? Okay, so let's work our way out of this. So temperature goes to infinity. What's the fraction going to do? I've got infinity in the denominator of a fraction.
0.
Yeah, so you're dividing by infinity. So that fraction's going to go to 0. And where's that fraction? It's in the exponent. So anything raised to the 0 is 1. Yeah, so I have e to the minus 0, which is 1. And now in the denominator, I've got 1 minus 1. Now it's going to go to that. So it's approaching 1 minus 1. And so Q is going to go to infinity. As the denominator starts getting close to 0, Q is just going to cruise right on up to infinity. And so as temperature goes to infinity, Q goes to infinity. As temperature goes to 0, Q does not go to 0, it goes to 1. And so now you can see how that works. And so this, again, the total vibrational partition function without 0-point energy is shown there. That's the one we've been working with. But at very high temperatures, notice it does kind of look very linear in temperature. Look at the behavior on the plot, right? Now we can be sure that after you get to 10 times, so temperature over the vibrational temperature, if after that's 10 or more, then it's linear, it's locked in. And so that's when we have this, just the Q approaches T over theta V. So whenever we say the temperature is greater than 10 times the vibrational temperature, then Q is simplified to this. But notice that doesn't go to 1 as temperature goes to 0, does it? So if we started cooling things down, once we got below the sort of cutoff of 10, temperature being 10 times theta V, then we need to switch back over to the equation on the left and start actually calculating it using the exponential piece. Now, how many vibrations are there in a molecule? You can see it on here somewhere. 3n minus 6. And so the interesting thing about partition functions is they're multiplicative. It's the product of all. So if I have the total partition function for a molecule, it's the partition function for translation times rotation times vibration. And vibration has 3n minus 6 terms. So instead of a sum, it's a product. It's the capital pi. So I have every vibrational mode has its own partition function. Because every vibrational mode has a different vibrational frequency, and it's going to have a different vibrational temperature and a different partition function. So I can store a lot of energy in the excitation of molecules in the vibrations because there's so many of them in a molecule. If the vibrations are low enough. If the vibrations are too high, then my partition function is 1 for that. So like the CH stretch, 3,000 wave numbers for the CH stretch, room temperature is 200 wave numbers. The partition function for the CH stretch is 1. So I'm really not storing any energy in the CH stretches. You know, if I'm trying to heat things up, my heat is going into translation, my heat is going into rotation, but it's not going into the CH stretch because it's just too high. It's too high of a shelf. I can't put any energy on it. Okay. And so with that 0-point energy, meaning if you define the 0 at the bottom of the potential surface, then that's the partition function. So I'll just show it just to have it in the notes. And so here we have now the Gaussian thermochemistry section where we have the vibrational temperatures added in. So if you look at the output file, you'll see the vibrational temperatures. And they list the lowest ones. In this case, the molecule only has 3, so they list all 3. But in a molecule like ethane or something, they'll list the twisty one. They'll list some of the bends. I think they list the lowest 6. Because those are going to be the ones that are going to be active, and then once you get past those, then you're probably going to have ones that all the partition functions are 1, so why list them? Okay. You get the frequencies in the frequency output, so you could calculate all of them, but in the thermochemistry section, they just list the lowest ones. So just review, we have 3 degrees of freedom, 3n total degrees of freedom, so 3 of those are translation, 3 of those are rotation, so we have 3 rotational constants. And then we have 3n minus 6 vibrational degrees of freedom. This molecule had 3 atoms. So we have 9 total possibilities. 3 translations, 3 rotations, and 3 vibrations. So this is everything in the molecule right here. And so then we have the partition functions. So Gaussian actually calculates the partition functions for us. And so here it shows them in a really weird format. It's kind of like engineering notation, not scientific notation. So you always start with 0 point something, and then times 10 to the is just d. So d is times 10 to the 4th, times 10 to the 11th, etc. So I went ahead and converted those into, whole numbers here. Yeah, so this is 0.228 times 10 to the 4th. So that's that number. And so these are the partition functions for this molecule for all the different motions. So we have the rotational, which was, again, we calculated this number earlier. We had the 3 rotational temperatures. We had the room temperature. We had the symmetry number. And we got 2228. And that was when I said, what are the units? And it was unitless. That was where that number came from. The translational. So Gaussian took into account the mass of the molecule and so on, the pressure, 1 atmosphere, and so on, calculated the translational, and the electronic, and the vibrational. If v equals 0. And so the total here is this times this times this times this. And so we have the total partition function for this molecule, which is an estimate of the number of energy levels populated at room temperature and 1 atmosphere pressure. And it's, let's see, 1,000, million, billion. So 33,399,000,000. Give or take a few. Okay. But the reason we're covering this in thermodynamics is when we excite that molecule, like if I want to store energy in that molecule to get it to push a piston, this is where I store the energy. So knowing how the molecule accepts and holds energy is important for thermodynamics. And so the most studied molecule on Earth is water for steam. So beginning in the Industrial Revolution, all the steam engines and everything, the engineers, they had whole books of steam tables, every nuance of pressure, temperature, and volume changes that they had for that molecule so that they could get it to do the most work possible. Okay. And so there may be other better working fluids, but water's abundant. And so we still use steam. We're still steam powered. It doesn't matter if you're using nuclear, coal, well, natural gas, I guess now it's using its own thing, but coal and nuclear and so on are driving our electrical system. They're spinning the turbines. The natural gas is new because it's actually a jet engine, like an airplane engine that burns natural gas and spins the generator. We'll get into that in the last bit of the course. So when we get back next time, we'll start with cahoots on all 3 of these. So yeah, so it'll be a great review.